Good morning, students. Today we are going for resonance in AC circuits. So generally in physics you studied what is a resonance. The phenomenon of resonance is whenever two bodies are vibrating each other, then the two bodies are under resonance. So like that, in a passive elements of inductor and capacitor which are connected to form as a electrical network or a circuit. So due to the AC supply, so AC supply means there must be periodic change in the supply voltages. So due to that, the frequency must be there. Due to this frequency, there may be a chance that the electrical network or a circuit can be gone into the resonating system. Under that condition, so you are getting the total impedance must be a pure resistance. So that means the net reactance value must be equal to 0. So at the same time, the value of current must be somewhat higher as compared with the normal condition of a supply given to the electrical networks. Okay, so the main resonating phenomenon for the electrical circuits is a applied voltage is given to a RLC series circuit So under that condition, a system frequency, so that is the natural frequency must be considered as F. So a sinusoidal current will flow through the RLC series circuit. So due to the small change in the voltage, there is a big change in the current. So this behavior we are understanding step by step with respect to the connections such as series resonating circuits and parallel resonating circuits. So this phenomenon is called resonance. Okay. So while you are going for the series condition of a resonating AC circuits, so I have taken R, L, C are connected in series with a AC voltage of V volts. A current of I amperes will flow through the circuit. So generally, whenever there is a frequency of XL must be equal to XC, or the voltage drop across the inductor must be equal to voltage drop across the capacitor, then the circuit will be resonated. So under this condition, the total impedance must be equal to pure resistance only. The total impedance must be equal to pure resistance only. So the voltage drop across the capacitor is equal to voltage drop across the inductor. So that means I gets cancelled. So what is Xc? Xc is 1 by C omega naught. And what is XL? XL is L omega naught, where omega naught is the resonating frequency. So by calculating this, omega naught is equal to root of 1 by LC. So if you want to write in terms of frequency, the angular velocity can be represented as F naught is equal to 1 by 2 pi root LC. So in terms of units of hertz. Okay. So under resonance, the voltage across the resistor is I into R, and the current flowing through the circuit is I. Both are in phase. And the voltage drop across the inductor will be in J omega axis upward direction, and the voltage drop across capacitor is in J omega axis downward direction, and the both magnitudes must be equal. So under that condition only you can get the resonance. So in resonance, the angle between V and I is 0 degrees. So that means the power factor cos of 0 is equal to 1. So you can say that under resonance condition, the power factor is unity, or a unity power factor will be there. The net reactance value must be equal to 0. The impedance value must be equal to pure resistance. Voltage drop across the inductor must be equal to voltage drop across the capacitor, and the supply voltage must be equal to your voltage drop across the resistor. So these are the conditions you are getting under resonance. Are you understanding? Okay. then the resonating current at resonating condition is I naught is equal to V by R. So I already told Z is equal to pure resistance only. So the circuit having only resistance. So the current flowing through circuit under resonance I naught is equal to V by R. Okay. So now to go for the impedance function of a RLC series circuit with omega. So for a RC circuit, Z is equal to R plus J omega L minus 1 by omega C, or you can simply write it as Z is equal to R plus J times of XL minus XC. So under resonating condition, so what is the frequency you are getting? Omega naught is equal to root of 1 by LC. So this is the omega naught value. The impedance is minimum and the admittance is maximum. So because the impedance is only pure resistor, only a pure resistor, the admittance is 1 by R. So we are getting a conductance value. So if you take R is equal to 0.1 ohm, then you can get the admittance is 10 mhos. So that means the impedance is minimum, the admittance is maximum under resonating condition. Under resonating condition, and the power factor must be unity. So now for your RLC series circuit, the current can be represented as magnitude of current is equal to V divided by root of R square plus XL minus XC whole square. So that is equal to V divided by root of R square plus L omega minus 1 by omega C, L by omega C whole square. So from that, the voltage drop across the resistor is I into R, so that is V into R divided by root of R square plus L omega minus 1 by C omega whole square. So similarly, voltage drop across the inductor, so I into XL, so VL is equal to V into XL divided by root of R square plus L omega minus 1 by C omega square. So similarly, voltage drop across the capacitor I into XC, so V into XC divided by root of R square plus 1 by L omega minus 1 by C omega square. So these are the voltage drop across the resistor, inductor and capacitor. So the characteristic diagram for the RLC series circuit will be like this. So here under resonance condition, so Z is pure resistance. So that means resistance never depends upon the frequency. So it is a constant line parallel to your x-axis. So x-axis we are taken as omega. So with respect to omega, the resistance is always parallel with some magnitude of R ohms. Okay. So then the impedance can be represented as what? R plus JXL minus JXC. So the impedance will be R plus JXL minus JXC. So where XL is L omega and XC is 1 by C omega. 1 by C omega. Okay, so as the omega is gradually increasing, as the omega is gradually increasing, so inductive reactance will be increases and capacitive reactance will be decreases. Inductive reactance will be increases and capacitive reactance will be decreases. So initially the capacitive reactance will be high as compared with the inductive reactance. So that's why the impedance will be highest at the initial and gradually decreasing. At resonance, the net reactance value must be equal to 0. So the impedance is pure resistance. After that, further increase in the omega, so the circuit will be act as a RL circuit. So that means inductance is more as compared with the capacitance. So the quite inverse is the admittance. So admittance initially it is minimum and you are getting maximum at resonance, then again it falls down. Again it falls down. So it is also similar to your current. So current is also like this only. So maximum value you are getting at resonance. After that it becomes downing gradually with respect to change in frequency of omega. Then what is XL? So XL is L into omega. So omega increases, XL is also increases. Omega is equal to 0, XL is also 0. So it is a straight line passing through the origin. It is a straight line passing through the origin. Then coming to the XC, so XC is equal to 1 by C omega. So omega increases, XC value will be decreases. So at 0 position, XC is a maximum value and gradually decreasing as omega is increasing. As omega is increasing. And this dotted line is XL minus XC value. So before resonance, the XC value will be very high. After resonance, the XL value will be very high. So this is the characteristic diagrams of a RLC series circuit under resonating condition. Under resonating condition. Then under resonance, the voltage drop across the inductor must be equal to voltage drop across the capacitor and the resonating current must be equal to V by R. So if you plot omega versus current, so the I0 value is maximum as V by R value. So omega is equal to 0, omega is equal to 0, the current will be 0 and it reaches under resonating condition. After completion of the resonance, again it falls down. Okay, so now we are going for the different values of resistors, how the current waveform will be. So first case, I have taken R1. So R1 is a very lesser value as compared with R2 and R3. So you can get a very narrow current. So R2 is greater than the R1 value, you are getting a medium band value, and R3 is very much greater than R1 value, then you are getting a pass band. You are getting a pass band. So this is the selectivity property of the resistance in such a way that for any electrical network under resonating condition, if the resistance is very low, you can get a very pass band. You can get a very pass band, and the resistance value is very in the sense the pass band means the current will be very narrow, and if the resistance is very high, so you can get a pass band of the currents. Okay, so this is the condition you are getting with respect to RL is less than R2, less than R3 conditions. So then coming to the most important thing is quality factor, or in case of a RLC series circuit, you can call it as voltage magnification factor. So this factor will magnify the voltage of a RLC voltage drops. So the definition of the voltage magnification factor, or quality factor can be the ratio of voltage drop across the capacitor or voltage drop across the inductor to voltage drop across the resistor. So it is denoted by Q naught. So Q naught is equal to voltage drop across the inductor at resonance or voltage drop across the capacitor at resonance divided by voltage drop across the resistor is same as supply frequency. Is same as supply frequency. So now Q naught is equal to, so I naught into XL divided by I naught into R, or I naught into XC divided by I naught into R. Or you can write it as Q naught is equal to L omega naught by R, or 1 by C omega naught into R. So now what is omega naught? The resonating frequency is root of 1 by LC. So if you substitute in the above equations, so Q naught is equal to L divided by R into root of LC, or 1 by CR into 1 by root LC. So finally for both equations, so you can get the Q naught value must be 1 by R root L by C. So this is the quality factor we are getting for voltage magnification in the voltage drop across the resistor, voltage drop across the inductor, voltage drop across the capacitor for a given voltage of V volts, AC supply to connection of your RLC series circuit. So next, coming to the condition for maximum value of voltage drop across the inductor by varying the inductance. Okay. So voltage drop across the inductor, already you know that VL is equal to I into XL. So for a RLC series circuit, I value is V by root of R square plus XL minus XC whole square into XL. So now we are going for the maximum condition, means differentiating with respect to the variable XL and substitute it to 0. So by differentiating the above equation, so dou VL by dou XL is equal to, so root of R square plus XL minus XC whole square into V minus V into XL divided by 2 into R square plus XL minus XC square into power of minus 1 by 2 into 2 times of XL minus XC is equal to 0. So we are going for U by V formula. By using that U by V formula, we are differentiating the equation VL with respect to XL derivative. Then after simplification, so R square plus XC square is equal to XL XC, or XL is equal to R square plus XC square divided by XC. So from this, the voltage drop across the inductor is maximum. We are going for the condition. So XC square is equal to XL XC minus R square. Then what is XC? XC is 1 by C omega. So 1 by C omega L whole square plus L omega L into 1 by C omega L minus R square. So finally the omega L is equal to root of, we are getting C into L minus C square R square under the root of the radical. So this is radians per second. Then coming to the condition for maximum value of VC by variation of XC. So VC is equal to I into XC. So I value is V divided by root of R square plus XL minus XC whole square into XC. So now we are going for the maximum condition. We have to differentiate with the variable XC and substitute it to 0 for the above equation. So dou VC by dou XC is equal to, we are using U by V formula. So root of R square plus XL minus XC whole square into V minus V into XC by 2. So under the radical we are writing root r square plus xl minus xc whole square power minus 1 by 2 into 2 times of xl minus xc is equal to 0. Then xl xc is equal to r square plus xl square, or xc is equal to xl divided by r square plus xl square. So now we are writing with respect to the capacitive frequency. So xc can be represented as 1 by c omega c is equal to L into omega c divided by r square plus L omega c square. So finally omega square is equal to root of 1 by LC minus r square plus L square. So these are the two conditions very important for the gate concept, because they will ask what is the frequency of the capacitance under maximum value. So similarly, what is the inductive frequency under maximum value of inductance voltage? So at that time you have to tell omega L is equal to root of 1 by CL minus C square R square, and omega C is equal to root of 1 by LC minus R square by L square. Then similarly, I am going for the condition for maximum value of VL and VC by variation of frequency. So initially inductive reactance you are varied, capacitive reactance you are varied. Now you are going for variation of frequency. So voltage drop across the inductor VL is equal to I into XL. So that is equal to V into XL divided by root R square plus XL minus XC whole square. So V into XL value L omega divided by root of R square plus L omega minus 1 by C omega whole square. So now we are going for the condition for maximum value of voltage when the variation of frequency is there. So dou VL divided by dou omega is equal to 0. So we are going for U by V formula for the above equation. So root of R square plus L omega minus 1 by C omega square into V into L minus omega L into V by 2 into 1 by root of R square plus L omega minus 1 by C omega square into 2 times of L omega minus 1 by C omega into L plus 1 by C omega square is equal to 0. So each term you are differentiating with respect to omega. So finally you are getting R square plus L omega minus 1 by C omega whole square minus omega into L omega minus 1 by C omega into L plus 1 by C omega square you can get. So then after going for the simplification, so R square plus L omega square plus 1 by C omega square minus 2 L by C minus L omega square minus 1 by C into L plus 1 by C omega square is equal to 0. So you are going for the next simplification. You can get R square plus 2 into 1 by C omega square minus 2L by C is equal to 0. So then the omega L value is equal to root of 2 divided by 2LC minus C square R square you can get. So this is the frequency variation for the condition for maximum voltage across the inductor. So similarly for capacitor, VC is equal to I into XC. So V XC divided by root of R square plus XL minus XC whole square. So that is equal to V into 1 by C omega divided by root of R square plus L omega minus 1 by C omega square. So now we are going for the condition for maximum efficiency when the variation of frequency. So dou Vc by dou omega is equal to 0. Then root of R square plus L omega minus 1 by C omega square into V by C into minus 1 by omega square minus V by C omega into 1 by 2 R square plus L omega minus 1 by C omega power minus 1 by 2 into 2 times of L omega minus 1 by C omega into L plus 1 by C omega square is equal to 0. So further simplification, so we are getting as R square by omega plus 2L square omega minus 2L C omega is equal to 0. So finally omega C is equal to root of 1 by LC minus R square by 2L square you are getting. So these are the 4 important derivations with respect to variation of reactance, either inductance or capacitance, with respect to frequency variation of inductance, frequency variation of capacitance. So then coming to the voltage versus frequency. So here before resonance, the voltage drop across the capacitor must be maximum. I already told before resonance the inductive capacitance will be maximum. After resonance the before resonance the capacitor reactance must be maximum. After resonance the inductive reactance will be maximum. So for that reason the voltage drop across the capacitor must be maximum before resonance. So after resonance the voltage drop across the inductor will be maximum. At resonance the voltage drop across the capacitor must be equal to voltage drop across the inductor. So this is the condition you are getting, and you are verified also. So what is your omega C value? Root of 1 by LC minus R square by 2 LC. So omega naught is what? Root of 1 by LC. So before resonance the capacitance will be maximum. So similarly, so here you are getting omega L is equal to root of 1 by LC minus 2 by C square R square. So after resonance only the inductive voltage will be maximum. Are you understanding? Then coming to the series RLC circuit as a selector. So here why you are calling as a selector means, so you can go for the frequency calculations with respect to bandwidth of the waveform. So what waveform you have to choose means the current waveform you have to choose, because for a RLC series circuit the current must be constant. So voltage drop across the inductor, voltage drop across the capacitor, voltage drop across the resistor, and your supply voltage are differed, and the total voltage must be equal to VR plus VL plus VC. So in a series we have to go for the current. With respect to that current we have to go for the calculation of bandwidth, and you have to correlate with respect to quality factor, bandwidth, and also resonating frequencies. Okay, so here with respect to the variation of frequency and current, so you are getting the current waveform will be like this. So here you can go for any bandwidth, but you have to take the bandwidth must be half of the power condition. Why you are taking half of the power condition means the maximum power is transferred from source to load when the total resistance must be equal to your internal resistance, or the total impedance of the load must be equal to internal impedance of the load complex conjugate. So under that condition we are getting VTH square divided by 4 times of RTH you are writing. So that power is maximum when 50% of the condition only. So that's why the resonating power can be represented as V square by R, and the maximum resonating current is I naught is equal to V by R under maximum power condition. Under maximum power condition, so 50% of the power you have to take. So I square R is equal to V square by 2R, or I is equal to V by root 2 R, or you can write what is V by R? V by R is I naught. So I naught divided by root 2. So root 2 is 1.414, or the reciprocal of root 2 is 0.707 into I naught. So at 0.7071 I naught is the 2 points we are getting. So 1 point is omega 1, 1 point is omega 2. These 2 points you can call it as half power frequencies. So W1 is lower half power frequency, W2 is upper half power frequency. Okay, so for finding these values, so I is equal to V by root of 2 into R, and also what is I for a RC circuit, RLC circuit, I is equal to V divided by root of R square plus L omega minus 1 by C omega whole square. So now we are substituting the RHS of equation 1 and equation 2. So V by root 2 into R is equal to V divided by root of R square plus L omega minus 1 by C omega whole square. So now the V gets cancelled. So you can go for the LHS and RHS simplification. So finally you can get 2R square is equal to R square plus L omega minus 1 by C omega square, or L omega minus 1 by C omega square is equal to R square, or L omega minus 1 by C omega is equal to plus or minus R. So omega square LC minus plus RC omega minus 1 is equal to 0. So this is your characteristic equation. The roots of the characteristic equation is plus or minus R by 2L plus root of R square by 4L square plus 1 by LC. So W1 and W2 are the roots of your omega only. So the omega 1 is the minus R by 2L plus root of R square divided by 4L square plus 1 by LC, and your omega 2 is R by 2L plus root of R square divided by 4L square plus 1 by LC. So if you multiply the omega 1 and omega 2, so if you multiply, they are complex. So in the sense A plus B into A minus B. So finally what you can get 1 by LC. So A minus B and A plus B. So you can get A square minus B square. So if you substitute, sum of the parts will be gets cancelled. You can get 1 by LC, which is same as your resonating frequency square. So omega naught square. So therefore omega naught square is equal to root of omega 1 into omega 2. In terms of frequency, F naught is equal to root of F1 F2. Also R by 2L in the radical is eliminated. So R by 2L whole square in the radical is eliminated. So then the omega 1 value, is omega naught minus R by 2L, because root of 1 by LC is what? Root of 1 by LC is what? Omega naught only. So omega naught minus R by 2L. So similarly omega 2. So omega 2 is equal to omega naught plus R by 2L. So these equations are most important. Omega naught is equal to root of omega 1 into omega 2, or in terms of frequency F naught is equal to root of F1 into F2. So similarly, omega 1 is equal to omega naught minus r by 2l, or omega 2 is equal to omega naught plus r by 2l. So now we have to go for bandwidth. So what is a bandwidth? Bandwidth is represented by delta omega. So it is the difference of half power frequencies. The difference of half power frequencies. So omega 2 minus omega 1. So what is omega 2? Omega naught plus r by 2l. And what is omega 1? Omega naught minus r by 2l. So if you substitute, so the omega naught gets cancelled. Finally you can get r by l. So delta f is equal to f2 minus f1. So that is equal to r by 2 pi l. R by 2 by L. So now we are going for the relationship between the bandwidth and quality factor. So already you know that the current can be represented as V divided by R plus J times of L omega minus 1 by C omega. So here I am taking R as common. V divided by R into 1 plus J times of L omega by R minus 1 by C omega R. So now L omega by R, I am multiplying and dividing by omega naught. I am multiplying and dividing by omega naught. So similarly 1 by C omega R, I am multiplying and dividing by omega naught. So that is equal to I naught divided by 1 plus J times of, so your Q naught. Q naught is L omega naught by R, omega by omega naught minus 1 by omega naught into RC is again Q naught into omega naught by omega, or I naught divided by 1 plus J times of Q naught into omega by omega naught minus omega naught by omega. So the quality factor, it always depends upon the frequency under resonance. Frequency under resonance. At the same time, if the omega value and omega naught value are same, then the total current must be equal to your resonating current only, because omega by omega naught minus omega naught by omega both will be 1. So 1 minus 1 is 0. So this value is multiplied by Q naught. There is no imaginary part, and the total I value must be equal to I naught only. So now the bandwidth is omega 2 minus omega 1, that is equal to R by L. I am multiplying and dividing by omega naught. So omega naught R divided by omega naught L. So that is equal to omega naught divided by omega naught L by R. So delta omega by omega naught is equal to 1 by Q. So Q naught is equal to omega naught by delta omega or 1 by S, where S is selectivity. So in any electrical network under resonating condition, you have to choose proper selectivity and you have to maintain good quality factor. Both you have to balance. So if the selectivity will be very poor, so that means you can get a pass bandwidth, and the quality factor will be very bad condition with respect to your ratio of VL by VR or VC by VR, because the pass bandwidth means current is very low. The current is very low. So that's why the selectivity property and the quality factor must be chosen with a good quality only. Okay, so this is the relationship between bandwidth, resonating frequency, quality factor and selectivity. Then coming to the parallel resonating circuits. So these are divided into three categories. So one is a RL RC parallel circuit, another one is a generalized parallel circuit, and the last one is a dual of RLC series circuit. RLC series circuit. So one by one you can go for the calculations of the frequencies. So here the first case you are taking RL and RC are connected in parallel. So RL plus JXL is the first branch impedance. RC minus JXC is the second branch impedance. Are you understanding? So in parallel case, so always you have to go for the admittance calculations. So first you have to calculate first branch admittance. So that is Y1 is equal to 1 by Z1. So 1 by RL plus JXL, and Y2 is equal to 1 by Z2. So that is equal to 1 by RC minus JXC. So for a parallel circuits, voltage must be same. The currents are divided into branches. Okay. So in a parallel circuits, what is the condition of resonance? What is the condition of resonance? So the condition of resonance in parallel circuit is the net reactance value must be equal to 0. So admittance is G plus or minus JB, where G is the conductance and B is the susceptance. The net imaginary part or net susceptance value is equal to 0. The total admittance must be equal to your total conductance value. So the power factor must be unity. So voltage drop across the one circuit to voltage drop across the second circuit is also same. The current values are divided because two branches are connected in parallel with respect to net current. So now I am going for the calculation of frequency. So total Y is equal to 1 by Z1 plus 1 by Z2. So 1 by RL plus JXL plus 1 by RC minus JXC. I am going for the rationalization. RL minus JXL divided by RL plus XL square plus RC plus JXC divided by RC square plus JXC square. So I am segregating the real part separately and imaginary part separately. RL divided by RL square plus XL square plus RC divided by RC square plus XC square plus J times of XC divided by RC square plus XC square minus XL divided by RL square plus XL square. So now this net reactance must be equal to 0. The net reactance must be equal to 0. So if you substitute, so you can get XC divided by RC square plus XC square minus XL divided by RL square plus XL square is equal to 0. So what is XC? XC is 1 by C omega naught. XL is L omega naught. So if you substitute 0, so after simplification, omega naught square L square minus omega naught square LC RC square is equal to L by C minus RL square you can get. So further simplification, we are getting the omega naught value. Omega naught value is equal to root of 1 by LC into root of the numerator value RL square minus 1 by LC divided by the denominator value RC square minus L by C. So here also the impedance you are calculating or the admittance you are calculating under resonance. The net reactance value must be equal to 0 means the total admittance is pure conductance only. So what is that value? Y naught is equal to RL divided by RL square plus XL square plus RC divided by RC square plus XC square, and the resonating current I naught is equal to Y naught into V. So this is the first case of your RL RC parallel circuit. So coming to the generalized circuit or a practical circuit. So here RL and XL are connected in series and it is connected in parallel with the capacitor. It is in connection with parallel of a capacitor. So now the admittance of first branch. So what is your Z1? Z1 is RL plus JXL. And what is your Z2? Z2 is minus J times of XC. Minus J times of XC. So calculate the admittance values Y1 and Y2. Then the net admittance value Y is equal to Y1 plus Y2. So 1 by RL plus JXL plus 1 by minus JXC. So that is equal to, so 1 by RL plus JXL plus J divided by XC. So go for the rationalization. So RL minus JXL divided by RL square plus XL square plus J divided by XC. Then you have to go for segregation of real and imaginary parts. RL minus J omega L divided by RL square plus L square omega square plus J omega C. So then RL by RL square plus omega square L square is the real part. And imaginary part is J times of omega into C minus L divided by RL square plus omega square into L square. So then according to resonance condition, net reactance value is equal to 0. So if you substitute net reactance value is equal to 0, omega naught into C minus 1 by RL square plus L square omega naught square is equal to 0. So omega naught C is equal to omega naught L divided by RL square plus L square omega naught square, or RL square plus omega naught L square is equal to L by C. So finally to go for the calculation of omega naught, so omega naught value is equal to root of 1 by LC minus RL square divided by L square. So this is the condition you are getting. So in this condition, if no resistance is there, so this value is 0. So if this value is 0, so it is omega naught is equal to root of 1 by LC only. So omega naught is equal to root of 1 by LC, which is a RLC series circuit resonating frequency, which is a RLC series circuit resonating frequency. Are you understanding? And similarly, the real part of your Y is RL divided by RL square plus omega square into L square. So you can calculate the omega naught value is equal to the previous equation. So that is RL square plus omega naught square L square is equal to 1 by LC. So Y naught is equal to RL divided by L by C. So that is equal to CRL by L, or Z naught is equal to, in terms of dynamic impedance, 1 by dynamic admittance is equal to L by CR. So in gate they will ask the practical circuits for most cases. So what is the dynamic resistance for a circuit with resistance, inductance, capacitance they can give. So at that time you have to go for Z naught is equal to L divided by C times of RL. And under resonating condition, so V by Z naught. So that is V into CRL divided by L. So this is your practical circuit. If resistance is also not there, then you can say that it is a tank circuit. Only inductance and capacitance, they are connected in parallel. So that also you can get the same values, replacing the resistance is equal to 0 in these equations. And finally, coming to the last case, so it is a RLC series circuit dual network. RLC series circuit dual network. Resistance, inductance, capacitance are connected in series with a voltage source. Is dual network is a current source with conductance, inductance, capacitance are connected in parallel. So here the currents are divided. The voltage must be same across the four branches. 4 branches. So this is the characteristic impedance. I have taken only 3 parameters, Z, Y and G. So you can go for other parameters also. So that is net reactance, that is net susceptance value, and you can go for the voltage values like that. So there is no big deviance from the characteristic impedance of RLC series circuit and this parallel circuit. So the overall admittance Y is equal to G plus J times of omega C minus 1 by omega L. So net susceptance value is equal to 0 under resonance condition. C omega naught minus 1 by L omega naught is equal to 0. Omega naught square is equal to 1 by LC. Omega naught is equal to root of 1 by LC, or in terms of frequency 1 by 2 pi root of 1 by LC. Same as RLC series circuit only. There is no changes. But here instead of voltage we are going for the current. Instead of voltage we are going for the current. That's all. There is no big changes. Similarly, in RLC series circuit, we are taken as a selector as current, because current is common. So in a parallel circuits, voltage is common. So we have to go for the half power frequencies with respect to voltage versus frequency. Voltage versus frequency. At what value you have to take? At half of the power value. What is the half of the power value? So that is 0.707 V naught value. So W1 is the lower half power frequency, W2 is the upper half power frequency. Then you can go for the omega 1 is minus G by 2C plus root of G by 2C whole square plus 1 by LC. And the upper half power frequency is omega 2 is equal to G by 2C plus root of G by 2C whole square plus 1 by LC. So what is bandwidth? Bandwidth is difference of two frequencies, omega 2 minus omega 1. So finally you can get G by C. So in series resonating circuit, the bandwidth you are getting is R by L. So the dual network is R is replaced by G and L is replaced by capacitor. So it is the dual network of your RLC series circuit only. So that's why the bandwidth you are getting is G by C. G by C. Are you understanding, all of you? So any doubts regarding in this case? Then come to the quality factor. So for a parallel circuits, the quality factor can be treated with current magnification factor, because the overall current is divided into different parallel branches. For that reason, you have to go for the quality factor in parallel circuit is current magnification factor. The current flowing through the inductor must be equal to the current flowing through the conductor, or the current flowing through the capacitor must be equal to the current flowing through the conductor. So quality factor Q0 is equal to IL or IC divided by IG. So that is equal to YL into V divided by GV, or YC into V divided by GV. So VV anyway gets cancelled. So you can get 1 by omega naught LG or omega naught C by G. So in RLC resonating case, Q0 is equal to R by omega naught L or omega naught CR. You can get by replacing G as R, L as C and C as L. So this is the condition you are getting. Then the quality factor is equal to omega naught divided by bandwidth. So that is equal to 1 by S. So where S is the selectivity of the circuit. So remember once again, bandwidth is omega 2 minus omega 1. Omega naught is 1 by root LC. So quality factor is L omega naught by R or 1 by C omega naught R, and the quality factor and your selectivity must be balanced to maintain good quality factor as well as good selectivity of the circuit. That you can get the relation with inversely proportional, so you have to balance it. So these are the main concepts of the RLC series circuit and RLC parallel circuits. Now come to the examples of a resonating circuits. So here the first example, you have to go for the calculation of resonating frequency for RLC series circuit. So the inductance they are given is 5 millihenry. The capacitance they are given is 50 picofarads. The resonating frequency F naught is equal to 1 by 2 pi root LC. So L is equal to 5 into 10 power minus 3 and C is 50 into 10 power minus 9. So by substituting that, so you can get 318 kilohertz. Then coming to the second problem, so you have to go for the calculation of Xc and Z at resonating condition. So here RLC they are given with a supply voltage of Vs. So under resonance the XL value must be equal to Xc. So that means so the Xc value is equal to 500 ohms. So now the impedance is R plus JXL minus JXc. So 100 plus J times of 500 minus J times of 500. So finally you can get 100 at an angle of 0 degrees. So you already know that under resonating condition the net reactance value must be equal to 0. The impedance is only pure resistance. So coming to the one more problem. So we have to go for the calculation of current I, voltage drop across the resistor, voltage drop across the capacitor, voltage drop across the inductor for the circuit shown in figure. So here under resonance the net reactance value is equal to 0. So the current I naught is equal to V by R. So what is V? 50 divided by what is R? 2.2 K. So by substituting that you can get 22.7 milliamperes. Then voltage drop across the resistor I into R. So that is I value 22.7 milliamperes into 2.2 kilo ohms. You can get 50 volts. Then voltage drop across the inductor VL is equal to I into XL. So 22.7 milliamperes into 1.0 kilo ohms. So you can get 22.7 volts. Then voltage drop across the capacitor. So I into Xc. So that is equal to 22.7 milliamperes into 1.0 kilo ohms. So you can get 22.7 volts. So under resonance, the voltage drop across the inductor and the voltage drop across the capacitor must be same. Okay. Then coming to the another example. So here they are given the resistance value is 2 ohms, the inductance value is 1 millihenry, the capacitance value is 0.4 microfarads. So you have to go for the calculation of resonating frequency, half power frequencies, quality factor, bandwidth, and also you have to go for the amplitude of current at omega naught, omega 1 and omega 2. So the first equation is for finding the resonating frequency, omega naught is equal to 1 by root LC. So that is equal to 1 by root of, so what is your L value? 1 millihenry. So 1 into 10 power minus 3 into what is your C value? 0. microfarads. 0.4 into 10 power minus 6. So you can get 50 into 10 power 3 radians. 50 into 10 power 3 radians. Then coming to lower half power frequency omega 1. So what is the formula? Minus R by 2L plus root of R by 2L whole square plus 1 by LC. So if you substitute the R value, the L value, the C value, in this equation. So finally you can get 49 into 10 power 3 radians. 49 into 10 power 3 radians. Then for calculation of omega 2, so r by 2l plus root of r by 2l whole square plus 1 by LC, substitute r value, L value and C value, then you can get the value of omega 2 is 51 into 10 power 3 radians. So kilo value we are getting for omega naught, omega 1, omega 2 with 50 kilo, 49 kilo and 51 kilo. Okay, so what is bandwidth delta omega? So delta omega is omega 2 minus omega 1. So 51 minus 49, you can get 2 into 10 power 3 radians or 2000 radians. Also the bandwidth is r by L. So there also you can get same value. What is your r value? 2. And what is your L value? 1 millihenry. So 1 into 10 power minus 3. Again you can get 2000 radians per second only. Then your next question is quality factor. So quality factor is Q naught divided by bandwidth. So Q naught value is Q naught is equal to omega naught divided by bandwidth. So omega naught value is 50 into 10 power 3 divided by 2 into 10 power 3. So finally you can get 25 is your quality factor. Or you can go for L omega naught by R or 1 by C omega naught R. You can get 25 only. There is no change. There is no change. Okay. So now we are going for the calculations of your currents with respect to the amplitudes omega naught, omega 1, omega 2. So already we are calculated for the values of omega 1, omega 2, omega 3. So at omega is equal to omega naught condition. So under resonating condition, I is equal to Vm by R. So what is the voltage they are given for this circuit? 20 sin omega t. So that means Vm sin omega t, Vm is equal to 20. So from that 20 divided by 2, you can get 10 amperes. Then omega is equal to omega 1 or omega 2, you can get the same answer only. So I divided by Vm divided by I is equal to Vm divided by root 2 into R. Root 2 into R. So 10 by root 2. So you can get 7.071. So why we are getting this equation means, so the omega 1 and omega 2 are half power frequencies. So half of the power condition means the current must be taken as Vm divided by root 2 times of R. So under that condition, you can get 7.07 amperes. So like this, you have to go for the calculation of a half power frequencies, resonating frequency, quality factor, bandwidth, or the current with respect to different frequency levels. With respect to different frequency levels. So next question. So a RLC series circuit, they are given the resonating frequency admittance of 2 into 10 power minus 2 Siemens. So the quality factor of the circuit is 50. The resonating frequency is 10,000 radians per second. We have to go for the calculation of RLC. So the admittance under resonance they are given. So that is 2 into 10 power minus 2. So resistance value you can calculate 1 by G. So 1 by G is equal to 1 by 2 into 10 power minus 2 or 1 by 0.02. So you can get 50 ohms. Then quality factor they are given. Resonating frequency they are given. So I am using the formula. Quality factor is equal to L omega naught by R. So here Q is known, omega naught is known, resistance just now we are calculated 50 ohms, calculate for L. So the L value is 0.25 Henry. So similarly using the same quality factor equation. So that is L omega naught, 1 by C omega naught R, 1 by C omega naught R is your Q value. So C is equal to Q by omega naught into R. Q is 50, omega naught is 10,000, R is 50. Then you can get the value of C is 100 microfarads. So they are asked to find the calculation of half power frequencies and bandwidth. So bandwidth can be represented as omega naught by Q. So what is omega naught? Omega naught is 10,000 divided by Q, 50. So you can get 200 radians per second. 200 radians per second. Then we are going for the calculation of omega 1. So omega 1 is equal to omega naught minus R by 2L. So R by L, you can write it as bandwidth. So 0.5 into bandwidth. So you can get 9900 radians. Similarly for omega 2, omega naught plus omega naught plus, this is plus 0.25 into bandwidth. So you can get 10,100. So this is the problem related, the solution for the circuit. Okay, so similarly we are going for the calculation of omega naught, R value, maximum value. So that is at frequency with respect to the quality factor we are calculating, and voltage drop across the capacitor at omega naught, and the voltage drop across the capacitor at maximum level for the given circuit. So here resistance value they are given is V naught, inductance value they are given is 5 millihenry, capacitance value they are given is 5 microfarads. So the resonating frequency omega naught is equal to 1 by root LC. So substituting, L is 5 into 10 power minus 3 and C is 5 into 10 power minus 6. We are getting 2000 radians per second. So now you can use the quality factor L omega naught by R or 1 by C omega naught R. So both the conditions you can get the same. So here I am using L omega naught by R. So omega naught 2000, L is 5 into 10 power minus 3, 5 into 10 power minus 3. So resistance value they are given is 50. So finally you can get the Q value is 2. So now we are calculating the maximum frequency. So that is omega naught root of 1 minus 1 by 2 Q square. So this is the equation you are getting for a RLC series circuit. So there you are calculated the Q value with respect to omega by omega naught and omega naught by omega. You are substituted one equation. From that relation you are getting a maximum value of omega. So by substituting omega naught is equal to 2000 and Q is equal to 2. So we are getting the value is 0.9354 into 2000. So that is omega naught value. So now omega naught for VC you are calculating. So Q into magnitude of Vs. So here the magnitude of Vs you are taking as 1. So then the peak voltage is 2 volts. So similarly for maximum value of Vc, so if you substitute Q into magnitude of Vs divided by root of 1 plus 1 by 4 Q square. So then you can get the value is 2.066 volts of peak. So like this you have to go for the calculation of your frequencies and quality factor and voltage drop across the capacitor with different frequency levels. So now coming to the RLC series circuit. So here the resistance value is 30 ohms, the inductance value is 20 millihenry, the capacitance value is 2 microfarads. They are given. So the applied the supply voltage is a sinusoidal voltage. so which has a constant output of 9 volts with all frequencies. You have to go for the calculation of resonating frequency, current at resonance, voltage drop across inductor, capacitor, quality factor, bandwidth of the circuit, and you have to sketch the current waveform. So this is the question. So the resonating frequency f0 is equal to 1 by 2 pi root of LC. So here they are given the L value is 20 millihenry and the capacitance value is 2 microfarads. If you substitute, you can get 796 hertz. Then the under resonance condition, the current I0 is equal to V by R. So V value is 9, R value is 30. So we are getting 0.3 amperes or 300 milliamperes. Then voltage drop across the inductor you have to calculate. So voltage drop across the inductor you have to calculate. So first you have to calculate the reactance of the inductor. So XL is equal to L omega naught. So by substituting omega naught is equal to 2 pi f naught. So 2 pi into 796 into L value 2 into 10 power minus 3, 20 into 10 power minus 3. So finally you can get 100 volts. So the voltage drop across the inductor I into XL. So 300 milliamperes into 100 ohms. So finally you can get 3 milliamperes. So 3 millivolts. 3 millivolts you can get. 3 millivolts you can get. Okay. 30 volts you can get. Okay. Then quality factor Q is equal to XL by R. So 100 divided by 30. So you can get 3.33 amperes. So then the bandwidth is omega naught by Q. So 796 divided by 3.333. So you can get 238 hertz. Then half power frequency is F1 is equal to, so F0 minus half times of bandwidth. So if you substitute, you can get 677 hertz, and the upper half power frequency F2 is equal to F0 plus half times of bandwidth. So we are getting 915 hertz. So this is the graph current waveform. Lower half power frequency is 677 hertz, upper half power frequency is 915 hertz. So under the bandwidth condition of 3 decibel is, so that is V divided by root 2 times of R value. So that is 212 milliamperes, and the maximum value of current under resonance is 300 milliamperes. So then come to the one more series circuit. So here they are given the resistance value 4 ohms, the inductance value 500 millihenry, a variable capacitance is there. It is connected to a supply of 400 volts with a 50 hertz frequency. So we have to go for the calculation of capacitance under resonating condition, and also you have to go for the voltage drop across the inductor and the voltage drop across the capacitor under resonance condition. So XL is equal to 2 pi f into L. So 2 pi f, so f they are given 50 hertz. So L value is 500 millihenry. So we are getting 157.1 ohm. So under resonance condition, so XL value must be equal to XC. So that is equal to 157.1 ohm. So what is C? C is equal to 1 by C omega naught. So 1 by 2 pi f into XC. So 1 by 2 pi into 50 into 157.1. So we are getting 20.3 microfarads. Then the resonating current I0 is equal to V by R. So 100 divided by 4, we are getting 25 amperes. So already you know that the voltage drop across the inductor must be equal to voltage drop across the capacitor under resonance. So here also you can calculate. So VL is equal to I into XL. So what is the value you are getting? 25 into 157.1. So that is, we are getting approximately 3.9 kilovolts. So similarly, voltage drop across the capacitor, if you go for I into XC, so there also you can get 3.9 kilovolts only. So this is the calculation for the different types of problems under series. Now we are going for the parallel circuit. So here a parallel circuit, so resistance they are given 600 ohms, inductance is 200 millihenry, capacitance is 120 microfarads, is connected to a voltage source, so that is 100 volts. So a current of Is will flow through the circuit. So IR is the current flowing through resistor, IL is the current flowing through inductor, IC is the current flowing through capacitor. So your question is, you have to go for the resonating frequency, quality factor, bandwidth of the circuit, and current magnification factor at resonance condition. So F naught is equal to 1 by 2 pi root LC. So by substituting L is equal to 200 millihenry and C is equal to 120 microfarads, so you can get 32.5 hertz. Then XL is equal to 2 pi F into L or L omega. So by substituting those values, we are getting 40.8. So it is same as XC. It is same as XC under resonating condition also. So then the quality factor I am using R by XL. So that is R by 2 pi FL. So 60 divided by 40.8, we are getting 1.47 value. Then bandwidth is equal to omega naught divided by R or F naught divided by omega naught divided by Q or F naught divided by Q. So 32.5 divided by 1.47. So you are getting 22 hertz. Once you calculated the bandwidth, the upper half power frequency and lower half power frequencies can be calculated. So F1 or F low is equal to F naught minus 1 by 2 into bandwidth. So if you substitute, you can get 22 point. So you can get 21.5 hertz. And similarly for upper half power frequency F2 is equal to F naught plus half times of bandwidth. So you can get 43.5 hertz. So the total current, net current is I naught. So I naught is equal to voltage drop across the current flowing through resistor only. So under that condition, supply voltage divided by resistance. So 100 divided by 60, you can get 1.67 amperes. So the maximum current or current magnification factor, you can use 1 by C omega naught into R or Q into IT. So 1.47 into 1.67. So you can get 2.45 amperes. So this is one way of calculation, or you can use IL is equal to V by XL. So that is equal to V by 2 pi FL. So there also you can get 2.45 amperes only. So because resistance, inductance and capacitance, they are connected in parallel, the voltage value must not changes, because parallel circuit voltage must be same. With respect to that, the maximum current is also same. So coming to the next problem. So here a parallel circuit is there. So the value of voltage they are given 100 sin omega t. R, L, C are connected in parallel. So you have to go for the calculation of omega naught, Q, bandwidth, omega 1, omega 2, and you are also calculating the power dissipation. So power dissipation means resistive power you have to calculate for the frequencies of omega naught, omega 1 and omega 2. Okay, so omega naught is equal to 1 by root LC. So L they are given 0.2 millihenry and C they are given 8 microfarads. So if you substitute, you can get 25,000 radians per second. Then the quality factor Q is equal to R by L omega naught. So R is equal to 8 kilo ohms. So omega naught 25,000 and L value 0.2 millihenry. So if you substitute, you are getting 1600. Then bandwidth is equal to omega naught by Q. So that is 25,000 divided by 16,000. So we are getting 15.625 radians per second. Then the lower and upper half power frequencies, omega 1 is equal to omega naught minus R by 2L. So R bandwidth by 2. So similarly omega 2 is omega naught plus bandwidth by 2. So we are getting omega 1 is 24.992 radians per second and omega 2 is 25.008 radians per second. So these are W1 and W2 values. So now we have to go for determination of power under resonance condition. So what is the Y value you are getting? Y value is 1 by R. So R is 8 kilo ohms. So the current you are writing V by Z. So that is equal to 10 sine omega t is 10 at an angle of minus 90 degrees. 10 at an angle of minus 90 degrees divided by 8,000. So finally you are getting 1.25 at an angle of minus 90 degrees milliamperes. So now we are taking the power at half of the power condition. So P is equal to half times of magnitude of current square into R. So 1 by 2 into magnitude of current 1.25 into 10 power minus 3 square into your resistance value 8 into 10 power 3. So finally we are getting that value of power is 625 milliwatts. 625 milliwatts. So like this you can calculate the power, or you can use the value P is equal to Vm square divided by 2 times of R, half of the power condition. So generally the power can be represented in terms of voltage means V square by R, half of the power condition means V square divided by 2 times of R. So here also by substituting V is equal to the value, magnitude value 10 square divided by 2 into 8 into 10 power 3. So we are getting 6.25 milliwatts only. Then for the lower and upper half power frequency conditions, so half of the power you have to take for omega 1 and omega 2. So again you are multiplying by 2 times. So it is the same as the maximum power formula. So P is equal to VTH square divided by 4 times of RTH. So P is equal to Vm square divided by 4 times of R. So 10 square divided by 4 into 8,000. So finally you can get 3.125 millihenry. So this is your 50% power of your original power according to maximum power transfer theorem. So like this you have to go for the calculations of the resonating circuits. Now come to the network functions. So any network can be represented in terms of Laplace transform variables. So the transfer function must be considered as the ratio of excitation to the response. So the transfer function can be represented as the ratio of excitation to the response. Okay, so in time domain behavior. So before going to the network functions, so actually there are different types of networks are there. One port networks, so one pair of terminals 1 and 1 dash is connected to a complex network. So two port network means two pair of terminals, 1 dash is one pair, 2 dash is another pair, is connected to a rectangular hollow complex network. So n port network, so such n terminal pairs are there, 1 dash, 2 dash, 3 dash, n dash, then you can call it as a n port network. So you have to go for the network functions with respect to the transfer impedances, so one port current to another port voltage, or another port current to one port voltage, or same port voltage to same port current, or you can go for the transferring between the circuits, coupled circuits. So all these comes under the pair of terminals with respect to network functions. Okay, so now to go for the network functions, so we have to use complex frequency. So complex frequency is denoted by S. Complex frequency is denoted by S. So S is sigma plus or minus j omega. So if it is a real, S is equal to sigma. If it is a complex, S is equal to sigma plus or minus j omega. So if the real part is 0, then the S value can be represented as j omega. So this is called the complex frequency. This is called the complex frequency. So here I have represented different waveforms with respect to different excitations. If omega naught is not equal to 0 and sigma is equal to 0, then this function is a sinusoidal function. It is varies with respect to time. If omega is equal to 0, sigma is equal to 0, so there is no complex frequency, so it is a DC excitation. It is a DC excitation. And the omega is equal to 0 and sigma is not equal to 0. So it is exponentially increasing or decreasing conditions. Exponentially increasing or decreasing conditions you can get. So the complex frequency in nature is also a variable in terms of complex frequency variables. So the real part sigma is treated as Nepper frequency, and the units of this is Neppers per second, and the imaginary part of your frequency is radian frequency, and the units of this frequency is radians per second. So frequency you are taking is a complex quantity, means real part will be there, imaginary part will be there. The real part is Nepper frequency, the imaginary part will be the radiant frequency. The units are Neppers per second. The units of complex value is radians per second, and the overall complex frequency is radians per second only. So it is S. It is denoted by S. Okay. Then coming to the network functions. So what is a network function? So for finding the impedance, what you are taking by Ohm's law, voltage divided by current. So if you write the impedance value, the voltage value, the current value in terms of S domain, then you can call it as a network function. And in this condition, you never take any initial conditions of the inductor or initial conditions of the capacitor, except a controlled sources. So dependent sources. So Z of S is equal to V of S by I of S, and similarly the admittance Y of S is equal to I of S by V of S, that is equal to 1 by Z of S. So Z of S is impedance transfer function, Y of S is admittance transfer function. So for a two-port networks, you can get transferring of one port variable to another port variable. So that's why you are calling as a transferred functions. So the impedance function and the admittance function can be also named with unique name as immitance function. So immitance function they are asked in the question means, so you have to write the impedance function and also the admittance function of the variables of a given circuit. Okay. So now we are going for the impedance functions. So for a resistor, you don't have any time dependent values. So R is Z of S and Y of S is 1 by R, or you can write it as G. So inductance can be represented as, so Z of S is equal to S into L. For admittance, 1 by Z of S, so 1 by S into L. So for capacitance, the value is 1 by C omega. So you are writing as 1 by S into C, and the admittance is 1 by CS. So you can get purely CS. So like this, the impedance functions you can get with respect to resistor, inductor and capacitor. So similarly, few more examples. So R and L are connected in series. Generally you can write the impedance is R plus S times of L. So the admittance is 1 by R plus S times of L. So similarly for RC circuit, so R plus 1 by SC. So S into RC plus 1 divided by S into C. So the admittance is SC divided by S into RC plus 1. So if L and C are connected in series, so SL plus 1 by SC. So S square LC plus 1 divided by S into C. So it is the impedance value. The admittance value is just reciprocal. SC divided by S square LC plus 1. So if it is a RLC series circuit, so R plus SL plus 1 by SC. So that is S square LC plus S into RC plus 1 divided by SC is the impedance value. The admittance value is SC divided by S square LS plus S into RC plus 1. So similarly, for a condition of your values with respect to transfer impedances. So if it is a two-port network, two pair of terminals must be there. So Z21 of S is equal to V2 of S by I1 of S. So similarly, the transfer admittance function Y21 of S is equal to I2 of S by V1 of S. So similarly, voltage transfer function G21 of S is equal to V2 of S by V1 of S. Similarly, current transfer function alpha 21 of S is equal to I2 of S by I2 of S by I1 of S. So this is I2, this is I1. So these are the impedance functions. So if you want to go for the inverse transfer functions, so inverse transfer functions means instead of Z21, you have to write Z12. So Z12 is equal to V1 of S by I2 of S. So similarly, admittance inverse transfer function Y12 of S is equal to I1 of S by V2 of S. So similarly, inverse voltage transfer function G12 of S is equal to V1 of S by V2 of S, and inverse current transfer function alpha 1 2 of S is equal to I1 of S by I2 of S. So like that, for a two-port network or a n-port network, you can go for the transfer impedances. So similarly, driving point impedance. So driving point impedance means Z11. So Z11 is equal to V1 of S by I1 of S. So driving point input impedance. So driving point output impedance Z22 is equal to V2 of S divided by I2 of S. V2 of S divided by I2 of S you have to write. So these are driving point impedances, and transfer impedance means one port voltage to another port current, or another port voltage to one port voltage. So like that you have to take different values are there, it is transfer. Same values are there, they are driving point. Okay. So now most important topic is poles and zeros of a network function. So any network function can be represented in terms of polynomials as S variables, So for example, n of s is equal to p of s by q of s. So a naught s power n plus a1 s power n minus 1 and so on a n minus 1 s plus an, where a naught, a1, a n minus 1 and an are the coefficients of your numerator. And these must be always real and positive. So similarly, q of s, b naught s power m plus b1 s power m minus 1 and so on bm minus 1 into s plus bm, where b naught, b1 and so on bm minus 1 bm are the coefficients of your denominator, and these are also must be a real and positive values only. Okay, so for finding the value of roots of your numerator, we have to substitute it to 0. So you have to substitute it to 0. So you can get the value of p of s. So by substituting p of s is equal to 0, the roots, let us assume p0, p1 and so on pn are the p0 is equal to 0 for the q of s. So p0, p1 and so on pm are the roots of the equation. And similarly, if you substitute p of s for 0, the roots will get z0, z1 and so on zn. So then the h is a scaling factor, so it is z0 divided by p0. So now n of s, by using the basic equation, can be represented as h into s minus z1 into s minus z2 and so on s minus zn divided by s minus p1, s minus p2 and so on s minus pm. So here, if you substitute these values is equal to 0, the roots you are getting is z1, z2, zn are zeros, and if you substitute this value is equal to 0, so that means n is infinity condition, then the p1, p2, the p1, p2 and so on pm values are poles of the equations. So whatever the zeros, whatever the poles of your given network function must be on the left side of the S-plane or at the margin of the S-plane, then the system is a stable system. If any pole or zero lying on the right half of the S-plane, then the system is a unstable system. So for finding the stability of the system in your control systems, anyway we will discuss in depth. So here I am just giving the basic knowledge of the network function with respect to poles and zeros. So let us take a simple example. N of s is equal to s into s plus 5 divided by s plus 2 into s plus 1 plus j1 into s plus 1 minus j1. So here the numerator is equal to 0. So p of s is equal to 0. So you can get s is equal to 0 and you can get s is equal to minus 5. The zeros are represented by small circles. So if you substitute, the value is n of s is infinity. So poles is equal to zeros you can get. So here s is equal to minus 2 and s is equal to minus 1 plus or minus j1. So complex conjugate you are getting. So poles are represented by cross symbol. So here complex conjugate is minus 1 plus or minus j1. So upper side of the j-axis, lower side of the j-axis you are getting, and another pole is at s is equal to minus 2. So here all poles are lying on the left half of the s-plane, and zeros, one is lying on the left half of the s-plane and another one is at the origin. So this system is a stable system. stable system. If any pole or any zero is lying on the left half of the S plane, then that system is a unstable system. Okay, so now coming to the Bode plot. So how we are going for the Bode plots? So Bode plots or Nyquist plots or polar plots must be considered with respect to your magnitude and phase angle. So let us assume a RL circuit. A RL circuit is there. That impedance can be represented as R plus J XL. So what is the magnitude? Magnitude is equal to root of R square plus XL square. So magnitude of impedance is R square plus XL square. So XL is L omega. So for different values of omega, we are calculating the magnitude. So let us assume the plot will be like this. So similarly, phi is tan inverse of XL by R. So the power factor for a RL circuit, power factor angle phi is equal to tan inverse of XL by R. So L omega naught by R with tan inverse. So for different values of omega, so if you go for the phi value, the waveform of phase will be like this. So this is your magnitude plot and this is your polar plot. So now coming to the significance of poles and zeros. So most important thing is the significance of poles and zeros you have to see. So the driving point impedance Z11 of S is equal to V1 of S by I1 of S. Okay. So for finding the values of your Z11 for numerator, you can get zeros. So that is N of S is equal to P of S by Q of S. So for finding the zeros, what you have to take? The numerator is equal to 0. So numerator is equal to 0 means voltage is short circuited. So under voltage is short circuited, the critical frequencies you are representing as zeros. So similarly, when the denominator is equal to 0, the Z11 driving point impedance will be infinity. So under that condition, Q of S is equal to 0. So you can get the critical frequency will be represented as poles of the function. So current is 0 means open circuited. You are calculating the values. Those are you are getting the poles of the function, and the numerator is 0. The voltage is short circuited. You are calculating the frequencies. Those are the zeros of the function. Vice versa for admittance function also. So what is admittance function? Y11 of S is equal to I1 of S by V1 of S. So if you substitute numerator is equal to 0, current is 0. You are open circuiting and calculating the zeros of the frequencies, and you are taking Y of S is infinity. So V1 of S is equal to 0. So voltages are short circuited. You are going for the critical frequency functions at a pole level. Are you understanding? So these are the most important things discussed with respect to the significance of zeros and poles. Anyway, it is a basic thing. I am not discussing in depth. In control systems, once again we are studying entire poles and zeros. What are the advantages and how you have to go for the stability of the system in frequency domain and also time domain analysis. Okay. Then coming to the necessary conditions of driving point impedance. So driving point means Z11 or Y11 or Z22 or Y22, like that. So these are single input, single output systems or multi-output, multi-input systems. Okay. So here the first thing is the coefficients. So A1, A2, AN, AM, or B0, B1, B2, and so on, Bm. Those are the coefficients of the polynomials P of s and Q of s. So these must be real and positive. So that is your first thing. Then the poles and zeros, if any complex is there, there must be complex conjugates. So only one complex value will not be satisfied for the necessary condition. If complex roots are there, it must be complex conjugates only. Then the real part of poles or zeros must be a negative or zeros. The real part of your poles and zeros must be a negative or a zero. So that means s minus z1, s minus z2, or simply s like that. Okay. So then if the equations are like that, then all the roots must be lying on the left half of the s plane, and also some of the roots, as s is equal to 0, they are lying on the margin. So that is at the margin axis or in the origin. So that is also a stable system. So then the P of s polynomials and Q of s polynomials, there is no missing terms. So for example, so s power 4 plus 2 times of s power 3 plus 3 times of s square plus 4 times of s plus 1 is equal to 0. So here s power 4 is there, s power 3 is there, s power 2 is there, s power 1 is there, s power 0 is there. So no polynomial powers are missing. Then it should be applicable for the necessary condition. So if any one polynomial is missing, then it is not applicable for the necessary condition. But so all even terms are missing or all odd terms are missing, that is also a necessary condition for your driving point functions. At the same time, the highest degree of P of s and Q of s may be differed by 0 or 1. For example, numerator s power 5 is there, denominator s power 5 is there, it is differing for 0. So numerator s power 5 is there, denominator s power 4 is there, so it is also differing by 1. It accepts the both conditions. If s power 5 and s power 1 is there, so it is not accepting the necessary conditions for highest degree or lowest degree also. So this is the necessary condition of the driving point impedance. So similarly for transfer functions also. So almost you can get the same thing only. So P of s and Q of s is a n of s value. So the coefficients of P of s and Q of s must be real and positive. Must be real and positive. So P of s and Q of s, if it is a complexness is there, the complex conjugates must be there. The real part of all poles must be negative and zeros. So that means it is lying on the left half of the s plane. We are not bothered about the zeros of the n of s equation. But in the driving point impedance, both must be there. So in the polynomials, so either the lowest order or highest order is missing. So all odd numbers are missing or all even numbers are missing. You can acceptable for poles, but the zeros must be any missing terms in the polynomial. So at the same time, the degree of P of s is smaller as 0 and is independent of the degree of Q of s. In the driving point impedance, it must be either 0 or 1, but here the degree of P of s may be small as 0 and is independent of degree of Q of s. So similarly, G and alpha transfer functions, the maximum degree of P of s is equal to the degree of Q of s, and Z and Y, the maximum degree of P of s is equal to degree of Q of s plus 1. So almost similar to your driving point impedance only. Then coming to the problems. So here they are given a circuit. So we have to go for the transfer function h of s. So v of s by v of s by v naught of s by vs of s. So the resistance and inductance are connected in parallel and it is connected in series with the Rs. So now Z is equal to R parallel with the inductance SL. So SRL divided by R plus SL. Then V naught is equal to by current division voltage division method Z into Z plus RS into Vs. So I am using the calculation of V naught, voltage drop across the inductor. So this impedance here calculated. This impedance here calculated. So that is S into RL divided by R plus SL. So total voltage is Vs. So this impedance and this impedance they are connected in series. So by using voltage division, V naught is equal to total voltage Vs into same impedance Z divided by Z plus Rs. So finally V naught by Vs is equal to Z divided by Z plus Rs. So what is Z? S into RL divided by R plus SL divided by R plus SRL divided by R plus SL. So finally you can get SRL divided by R RS plus S into R plus RS into L. So like this we have to go for the transfer functions. So here they are given a circuit. So here also you have to go for h of s value, v naught of s by v of s. V naught of s is the voltage drop across the capacitor. So the two parameters R and C are connected in parallel and it is connected in series with the inductance L. So I am calculating the Z. R parallel with the capacitance 1 by Cs. So R into 1 by Cs divided by R plus 1 by Cs. So finally you can get R divided by 1 plus S into RC. So now this impedance here calculated, that is connected in series with Ls and applied voltage is Vs. Voltage drop across the impedance is V naught only. So by voltage division, V naught is equal to Z divided by Z plus SL into Vs. So H of S is equal to V naught by Vs, V naught by Vs. So Z by Z plus SL. So what is Z? R by 1 plus S into RC divided by SL plus R by 1 plus S into RC. So finally you can get R by S square L RC plus SL plus R. So like this you have to go for the calculation. Next problem. So here also you have to go for the calculation of H of S, V naught by V of S. So V naught of S by V of S. V naught is voltage drop across the 5 ohm resistor. So VI is the input voltage. So here the capacitance and resistance are connected in series and this is connected in parallel with the 1 ohm farads. So the capacitance values and the capacitance values I am writing in terms of S domain. So 1 by j omega c. So that is 1 by j omega is S only into C value 0.1. You can get 5 by S. Similarly 0.1 farad. 0.1 farad we are getting 10 by S. So the original equation we are representing like this. So 0.2 farads we are writing as 5 by S and 0.1 farad we are writing as 10 by S. So here these two are connected in series, these two are connected in parallel, this is connected in series with 2 ohms. So Z is equal to 10 by S parallel with 5 plus 5 by S. So finally we are getting 10 into S plus 1 divided by S into S plus 3. So once you calculated this total impedance, so V1 is the node voltage. So Vi is the input voltage. So you are going for the calculation as V1 is equal to voltage division total voltage Vi into Z divided by Z plus 2. So V0 is equal to what? Now you are calculated V1. Now you are calculated V1. So V1 is this voltage. So now V0 is equal to V1 into same resistance divided by sum of the resistance they are connected in series. So 5 divided by 5 plus 5 by S into V1. So finally you are getting S by S plus 1 into Z by Z plus 2 into V1. So here the Z value is how much? 10 into S plus 1 by S into S plus 3. So if you substitute the H of S value V1 by Vi is equal to 5S divided by S square plus 8S plus 5. So like this you have to go for the calculation of the transfer functions. So now coming to the one more problem. So you have to go for the calculation of Vc by V. So V is the input voltage, Vc is the voltage drop across the capacitor, and also you have to go for plotting of poles and zeros. So at node 1 applying the KCL. So here 3 currents are there. One is the entering current, 2 are leaving currents. So V is the node voltage. So Vc minus V divided by 4S. Vc minus V divided by 4S. So this is your first current. So Vc by 8 is one current, and Vc by 2S is your another current. So whatever the node voltage is same as your Vc only. So finally the value we are getting is Vc by 4S minus V by 4S plus Vc by 8 plus Vc into S divided by 2 is equal to 0. So I am taking Vc as common, 1 by 4S plus 1 by 8 plus S by 2 into V by 4S, or Vc is equal to 4S square plus S plus 2 divided by 8S is equal to V by 4S, or Vc is equal to V into 2 by S plus 4S square. So Vc by V is your question. So Vc by V is equal to 2 divided by 4S square plus S plus 2. So this is your H of S value. So it is a second order equation. We have to go for the partial fractions. After going for the partial fractions, the value will be 2 divided by S plus 1 by 8 minus J times of root of 31 by 8 into S plus 1 by 8 plus J times of root of 31 by 8. So complex conjugates are there. Poles are represented by cross symbol. So this is your S plot. So this is your S plot for the given transfer function. So similarly, so how you have to go for the Bode plots or magnitude and phase plots? Here I have taken a Bode plot. So the given transfer function is 10 divided by 1 plus j omega into 10 plus j omega. Okay, so H of omega is equal to, I am dividing 10, so 1 by 1 plus j omega into 1 plus j omega by 10. So the magnitude value we are writing as in terms of decibels. So minus 20 log 10, 1 plus j omega, minus 20 log 10, 1 plus j omega 10. So here by varying the omega value from 0 to infinity, so you can get the Bode plot of magnitude waveform will be like this. So similarly for your given transfer function, so the phi value, so phase angle value is minus tan inverse of omega by 10. So by varying omega from 0 to infinity, So this is your phase plot. This is your phase plot. So similarly, another example. So h of s they are given, or h of j omega they are given 50 divided by j omega into 5 plus j omega. So finally, I am going for multiplication of 5, both the numerator and denominator, by taking common. So 10 divided by j omega into 1 plus j omega by 5. So here the magnitude you have to write in terms of decibels, and phase angle you have to write in terms of tan inverse. So and substitute omega is varying from 0 to infinity. Then this is your magnitude plot and this is your phase plot. So like this you have to go for the different magnitude and phase plots. For a particular circuit you have to go for the transfer function h of s value, and the resonating frequencies, series and parallel combinations. The problems here analyzed, and you have to know, and you have to use the different textbooks to get more knowledge in the subjects. So different problems you have to consider, and you have to solve with the same concept whatever I teach in this session. So if you are having any ambiguity or if you are having any doubts, so you can ask. So I will explain point by point. Thank you one and all.